So here's a point charge of magnitude q, right? And so the question was, what about non-uniform or non-constant electric fields? This is what we call a radial field, right? That varies. Its strength varies. You can tell by this picture. How can you tell the strength of the field varies? The distance between the lines changes, all right? So or what we call the electric field line density changes. So we could say at a location right here, there's an electric field strength that is, anyone? You should all be yelling it right now. That'd be awesome. Right, KQ over R squared. Very good. But we can also, at this location, talk about a different quantity, which is electric potential. And the electric potential at that location is KQ over R. Now, out here, we'll call that R1. Right? Out here, where this distance we can call R2, there's a different value of potential, which is just KQ over R2. And it doesn't matter at all that these are different like directions away from the charge Q. All we care about is how far away from it we are. And that means that there is a potential difference between points 1 and points 2. And if there's a potential difference between 2 points in a field, what does that mean? No. Well, that's if there's more than one charge. Right? We could find the net potential for more than one charge by doing the K parentheses Q1 over R1 plus Q2 over R2, blah, blah, blah. Right? But what we say here is, if we were to take, I don't know, let's say a little positive charge from here to here, what would that require? It would require work. All right, so the work would be equal to Q times delta V. So this is a little charge Q. The lowercase q typically talks about charges placed in fields or charges that feel the effective fields. All right, so this thing, well, if we want to know the work done, we go Q, and delta V is, well, V final minus V initial. So this would be Q, V final is V1 minus V2. Or work is Q times K Q over R1 minus, whoops, Q times K Q over R2. Or really, we're saying K Q Q over R1, K Q Q over R2. And what's K Q Q over R tell you? Potential energy. So we're saying that work is a change in potential energy. U1 minus U2, or delta U. Okay? What?
If the charge infinitely far away, wouldn't
And that's a very, very common one. What if the charge comes from infinitely far away? Well, then what happens to one of these terms?
Zero.
Yeah. So if we say something about, how about this? Work to bring Q from infinitely far away. That means that this one goes away. And then we just end up with the potential energy of that final point, or of the two-charge system when Q's at that final point. Yes, sir?
In which scenarios do we make work positive and negative for this?
Well, In any scenario, the question is when do you use sign and when you don't, and when do you not? All right, you don't use sign. Anyone? Anyone? With vectors, because the sign of the charge draws the vector for you. If you're doing scalar stuff, like work, like potential, you do use the what do you call it, the sign of the charge. Okay. This work would have to come out positive, right? Because the potential here is smaller than the potential. The potential here is smaller than the potential here. So when you do V1 minus V2, you get a positive number, and then Q is a positive number, so work will be positive. Okay, so scalars use the sign. Vectors don't use the sign.
Well, I remember there was something like when we were bringing it to the charge, we would like hold it back.
Yeah, so that's and that's, I mean, it works for this example too. I know this one's going to be positive because for this positive charge, right? If I want to move it from here to here, or really if I want to move it in the against the field's trying to push it back to where it came from. So I physically have to push this way, through some distance from here to here. And if I push in the direction that I'm moving it, that's positive work, right? If it were a negative charge that we let go here, right, the field would make it go and do that, right? I'd have to end up pushing it back that way as it moves this way. That's negative work. Should we touch on anything besides E and M? I mean, E and M, huge part of it. I know. I will say this. Let's look at one more of these. I mean, I'm happy to do lots of E and M because it's a while ago and it's a ton of stuff. Let's say that we have a Q1 like that, and let's say that we have Q2 like this, and we have a location here. R1, R2. If we want to find the net field at that location, first step is draw it. All right, so E1 looks like, points to your left toward negative charge. E2 looks like down away from positive charge. I don't know how big to make these because I don't know what Q's are. Okay. The net field is going to point like that, where we could write an expression for the net field as we got to Pythagorate those. Okay. So that's going to be KQ1 over R1 squared, quantity squared, plus KQ2 over R2 squared, quantity squared. If we want to find the net potential at that location, anybody? Well, the R's aren't squared, and it ain't a vector. So all we do is just say, well, I'd write it as V2 minus V1. I'm using the sign of the charge here. So this just turns into KQ2 over R2 minus KQ1 over R1. Now notice, since I write minus here, I wouldn't put in the negative for what Q is here. I'd use the magnitude of Q. Okay? And then you could have, how much work would be required to bring a charge from really far away to that point. You do Q times that. Or we could say, all right, how much force, therefore, is exerted on a charge that we call Q there? What's the net force exerted on this charge? I would do it as this, Q net E. Right, so we just use this whole expression and then just chunk a Q on the front of it, and we got the net force. Okay? Just like the work to bring something from infinitely far away would be Q times net V.